I'm starting the live stream. Hello, I think I forgot to press go live for a moment there. Have I plugged in my microphone? Yes, I have. That's a good start, isn't it? Hello, Maths22222. How's it going, everyone? Are you all right? I've got a probability question today, or maybe it's a counting problem, I don't know. Here's a maths problem on the board. Herb's here too, hi Herb. Here's a counting problem on the screen. The idea is that we're going to count some property to do with subsets of a given range of integers. This is a problem that someone on a summer school showed me this week. So in time-honoured tradition, we did this last time, didn't we? I've stolen a number theory question from summer school that someone showed me, and we're going to try and solve it. Hello, Mary. Good to see you. Right. Okay. Here's the story with this one. The student showed me this problem, said that they solved it, and then I solved it using the same method, and then we were happy because we had the same answer. Somebody else ran some computer code to try and verify this by checking some randomly generated subsets of size 12 from 100 integers, and they got a different answer. And then after some arguing, we all went home and each individually realised that we were wrong about the maths that we'd done. So I had one attempt at this, I was wrong, but then later I had another attempt that I think is right. So I'm going to try and work on that. Work on correct maths rather than working on wrong maths. Hello to Neutrino in chat as well. Hi to people watching, and this seems like a good point to say thank you to 404 not found 19 for following the channel yesterday. I wasn't live yesterday, before whenever you like. Never a bad time to follow the channel. If you follow, I think you can maybe get notified about the random times that I've decided to do this. Usually 2 o'clock on a Sunday. I think I'm just doing 1 hour today. Got something going on at 3 o'clock. Oh, that chat message is slightly outside the box, isn't it? That hasn't quite worked. Good. Right. Okay. So maybe first I'll show you, just as a joke, a method that doesn't work. So put a note there so we don't get confused. The following does not work. So 100 choose 12 choices of 12 overall. That's sort of how many ways there are to choose 12, and then we should count how many of them have 4 consecutive integers. And the approach that does not work for this is a permutation of. So if you have to have 4 of them, oh my goodness, how have I done that? Permutation of 4 of them locked together, 8 more, 4, 5, 6, 7, 8. So that's 4 together, 8 more separately, and then 12, so 88 more that you don't pick. Don't choose these ones. The idea being that 4 together, if you have 4 together, then I'll draw a ring around it and shuffle. So if I shuffle these symbols, there are 97 symbols now if I keep these 4 locked together. 97 symbols, because I had 100 things that you play with before, but now if I lock them together, then I'll have 97, 1, 2, 3 kind of missing, 97 things to shuffle around. And if I think very carefully about shuffling 97 objects where 8 of them match, and another 88 of them match, then I get some number. But this approach doesn't work. Maybe chat can tell me why. It took us quite a while on the summer school to work out why this doesn't work. Then you would do a ratio, right? You would do the ratio. Just to finish off this method that doesn't work. Hello, Neutrino. Thanks for the subscription. Oh, mostly because I get to watch the animation again. Great stuff. But you're also almost a year, 11 months. Loading ready run have a joke that however long somebody subscribed for, they describe it as almost a year. Right. Yeah, so you could have 4 consecutive in the other 8, and that is oh no, because then you'd have double counted that. So oh no does some double counting. So things like you selected 8 like this with some other stuff. Maybe there are 2 ways to draw the box in, I suppose. I can't be bothered to draw the other 4. They're just over here somewhere. There you go. There's 2 ways to draw the box. Or maybe more than 2 ways to draw the box. If these are 8 all in a row, it's pretty unlikely. But if there's 8 in a row, then there's loads of ways to draw that box of 4. Those are all the same choice, right? The same choice of which 12 numbers came up. It's not remarkable twice, but you've counted it twice by having 2 different permutations. The way that we should have spotted this is by looking at smaller examples. So we should have spotted this as wrong, because if you have a very small number of cards, like 5, and you choose 5 of them, then you're guaranteed to get 4 in a row because you've chosen all of the numbers. This method gives you a probability that's larger than 1. I think it gives you a probability of 2, because there are 2 ways to permute 4 and a 1. Oh dear. Yes, 2 ways to permute 4 and 1, divided by 1 way of choosing 5 from 5. So if you switch the number 100 down to 5 and the number 12 down to 5, then you should get 1, but this method actually gives you the probability 2, which is not a sensible answer. So this does not work. If you've just joined us, don't look too closely at this. It's a method that doesn't work for a counting problem. Different ways to fix this that I've thought about a little bit. I thought I'd chat through with you in chat, actually. I thought about allowing for the double counting, to try keeping track of all of the sorts of double counting that we've done. But there's so many. I made a list of about 16 different sorts of coincidence that might have happened. Things like you have a string of 5 and a string of 4, because then there are 3 ways that you might have chosen to draw a circle around 4 of the 4 in a row. And it's pretty unlikely that you have 5 in a row and 4 in a row, but you've triple counted it, so these things add up. If you have all 12 in a row, then there are 9 ways to circle 4 in a row within that 12 in a row. So it's sort of really annoying that the amount of overcounting you do in different cases is different in different cases. Plus also, if you want to try and do those 16 sub-problems for overcounting, the obvious thing I think to do would be to do something like this, and that includes more overcounting. So each of these kind of sub-problems to allow for coincidences like overlapping sets of 4 or multiple sets of 4. Each of those sub-cases would involve lots more sub-cases, and sort of maybe then some horrible inclusion-exclusion sort of thing. Yeah, so cool. We'll be pleased to know that I'm not doing that. Instead, the way that I think I've solved it is with recursion, which I should have thought of earlier. So I guess this is a little lesson that we thought lots of it's kind of clever choosing stuff, but maybe I should, instead of making this more complicated, step back and try and write down some recursion relations. There's probably a third way, which you might like to think about at home, which is that possibly this is just some sort of stars and bars problem, and I should change my vision or something to change what I'm looking at so that the things I'm choosing are different. And then maybe there's some way to do this with just choosing. But I haven't thought of that yet. So I'm going to show you my recursion, which I think works. Let's go bold. I'm going to write the following does work. Let's copy the question down for people who join the stream in a second. Yep. There you go. Oh, I don't want to comment. I'm commenting all the time out loud. I don't need to type a comment. Okay, so I think the following does work. And then I think. So I've been thinking about this with different numbers in, where if you choose 12 cards, but the numbers only go from, if you choose 12 numbers, sorry, originally it was a card game. If I've been saying cards, it's because I've been thinking about cards. This is related to the card game Mind, where you have 100 cards, and it's pretty bad if you have consecutive numbers, which makes the game slightly harder. Anyway, that's the context. I've been thinking about this with different numbers of cards and how many are chosen, or integers and how many are chosen, different values of 12 and 100. It's got two variables that you put in. And ideally, you try and find a way to link these problems together for different numbers. So if you can relate the problem with these huge numbers down to a version of the problem with smaller numbers, then, well, that's good because you're making progress. If you know about mathematical induction, then you know about linking problems back to the previous problem. So maybe you've seen something like that. I would like to do something like that with this. But I think it's a bit tricky because we've also got this number 4 in here. Maybe I should circle that as well. I don't know. Okay. So I think it's, what do I want? I want a function of n and k be the number. Maybe I should do probability. I'll do number. Number of ways to choose k integers from 1 to n such that there are 4 consecutive integers. Okay, the number of ways to choose. So I'm replacing this this green thing up here, this number 100. I would like this first argument to be 100 eventually. It's kind of n. And I would like this number k to eventually be 12. This way to choose 12 integers, not distinct integers, but fine. Let's put the word in. Distinct. I wasn't trying to remove a default. Okay. So I want f of 112. Okay. Let's see. Can anyone in chat tell me some values of f, nk with small numbers, or special cases that you can think of? This problem is easier with small numbers. This is the big idea. Easy with small numbers, and then the problem we actually want to do has large numbers. So bridging the gap between small problems and large problems. But I think there's some small numbers that we should think about first. I don't know. Maybe chat tell me. I think like if n is similar to k or small. Yes. Oh, there you go. Maths and at the same time have told me that if you have 4 cards and they're called in there as well. Good. Okay, here we go. If you have 4 cards, so 4 numbers, and you choose 4 of them, I'm going to keep saying cards. 4 numbers from 1 to 4, and you choose 4 of them, then there is one way in which you will get 4 consecutive integers, because there's only one way of doing that. And it happens to have 4 consecutive integers. So, yeah, Akil would like to think about 5 cards, choose 4. So if you choose 4 of them, then, here are my 5 fingers, you might choose these 4, in which case we're good, we've got a consecutive set of 4, or you might choose these 4, if you were looking for ways to choose 4 consecutive numbers. So I think that's 2. That's not a probability of 2, that's the number 2. There are 2 ways to do it. Overall, there are 5 choose 4 ways to choose 4 of these 5 fingers. Oh, we're getting there, which is 5. So I think it says that if you have numbers from 1 to 5 and you choose 4 of them without repeats, then you have a probability of 40%, 2/5, to see 4 in a row. Because there are 2 ways to do it out of the 5 ways total. I'm tracking, if you like, I'm tracking the numerator, and then much later I'm going to have to divide by some horribly large number. So that'll be fun. Okay, what have we got? 4, 4 and 5, 4. We'll probably do some others though. So if I make the numbers smaller than 4, if I make the numbers smaller than 4, smaller than 4, then the number is 0. I don't care about k. If k is smaller than 4, then the number is 0. So if n or k is small, yeah, then I get 0. If n and k are equal, so if you choose all of the numbers from 1 to n, then you get 1, provided that n is larger than or equal to 4, so that it doesn't contradict with this stuff about small numbers. If you have 4 or more numbers and you choose all of them, then you will get, well, you will get 4 consecutive integers for sure, but there's only one way to do that because there's only one way to choose all of the numbers. Okay, this feels pretty good. We've got some examples in nk space. Just trying to visualize where these live. In nk space, you've told me about ones where you told me about 4, 4 first, which lies about here, and then we thought about ones on the diagonal of n equals k, and I'm happy for n smaller than 4. If n is equal to 4, I'm going to have to think a little bit, but if n is smaller than 4, I'm happy. In this region, I know what's going on, and in this region, for k smaller than 4, I know what's going on, you're going to get 0. 3, 3 is also another case we get 0. All of these things with 3's in. Okay, so you've got some integers, and if they get smaller than 4, then no way, it's rubbish. Okay, the ones we want are, well, we want sort of 100, 12 is over here somewhere. The link, by the way, for this visualization I'm trying to do is when you see a function with 2 inputs, the normal way to write that is with a comma between the inputs and brackets around the outside. But if you put your hand over the f, that's also how you write coordinates. So you could think about this being a function that takes a kind of vector as an input, or coordinates of a point as inputs. And I'm trying to visualize which inputs can we deal with. That link being, this is 100, 12, and I would like f of 100, 12. There's a bit of an abusive notation, right? That I'm not really saying those brackets are the same thing, but this isn't just f multiplied by a vector. That's not what I'm doing. Okay, quick. I would like 112 though. So, tricky thing is that we need a relationship between these values. Ideally, it's going to relate back to smaller values. From my point of view, that's that way round, but from you and on the screen, it's like this way. So if we can relate something back to have smaller problems to get back to this corner of the picture, I would accept going that way, and I'd accept going down, but if you can relate it to problems that are further towards that corner, then eventually we'll get to a problem that we can do. That's how induction works, and it's how this sort of thing works as well. Right. I've spotted, by the way, that if n is less than k, then there's just no ways to choose, so there's no ways to get 4 consecutive integers. So I'm going to put 0 over here as well. I'm going to say over here I'm pretty happy. If n is small, that's this side. So the shaded area is stuff that we can do already. It's pretty good. Should we try a problem where k is greater than 4? Yeah, let's see if we can reason about that. I have a link between these problems that will come in handy in a moment, which I think works. Part of the test here is whether I can convince chat that I've solved this problem. Neutrinos just got back. N minus 3 plus n choose k minus 4. I don't think you're stupid. You're going to need to give me a reason why it's this. I like the divided by n choose 4, I think. Maybe I do. Maybe that's right. Where's the n minus 3 come from? I need you to break it down. There's probably an idea there. Maybe I should say now that I'm not aware of my method that I'm about to do doesn't give me a neat and tidy answer, so if anything's possible, I don't know. Neutrino's going to tell me how to do this problem in a second. Right, okay. I'll quickly try and do my version. So my version goes like this. Think about whether n itself is chosen or not. If it's not, then you need 4 consecutive numbers. 4 consecutive numbers chosen from 1 to n minus 1. If n's not selected, you've got to pick. Well, I suppose you need 12. Sorry, you need k consecutive numbers chosen from 1. No, rubbish. You're choosing from 1 to n minus 1. Yeah. Yeah, neutrino, your method. Okay, so thinking about where the block of 4 consecutive numbers is, I think is a good step that almost gets us there. I have it up here somewhere, I think. If you think about having 4 consecutive numbers as a block, where you track where's the starting number, maybe this is what you're saying, I'm not sure. If you track where to put it and then choose the remaining k minus 4 afterwards, there's a problem that we're double counting ones where there are 2 blocks of 4. Because if you have 2 blocks of 4, then it's not unique, this definition of where does the block of 4 start. There's kind of multiple choices. So if you count all of the possible choices of where the block of 4 might start, some of those end up being the same selection of 12 numbers. Because you counted an example where it starts here and an example where it starts there simultaneously, even though it's the same. So this is a slight overcount. If you care about the numbers, this comes back as giving a probability final answer for the question is about 1.2%, whereas the correct answer is about 1.1%. It's a tiny difference, which is why, oh gosh, earlier this week, I don't know if any of them were watching, but earlier this week we had quite a lot of back and forth with the people writing the computer code, because 1.1 and 1.2 are really close together. Turns out the computer code people were correct. 1.1 was the right answer. And people are going to switch off now. They know that 1.2%, 1.1%, those are kind of the same thing. What's the big deal? Depending on the numbers, you might have bigger out by more. Okay. Right, so my new approach is to think about whether that last number is chosen or not. If not, then you've got to make this happen. If you're going to make 4 consecutive numbers, you've got to have it. If not, then you need 4 consecutive numbers. And I'm going to go out of, because I'm going to go out of k integers chosen from 1 to n minus 1. Okay, if you don't pick n, then itself, then you've got k to pick, k choices, k numbers that you're going to pick from 1 to n minus 1. You still want 4 consecutive numbers, so that's there are, well, not quite a lot of ways of doing that. M minus 1 k ways to do that. So that's pretty good. This is starting to feel like the number of ways to succeed if you have cards from 1 to 100 is a bit like, pretty similar to the number of ways to succeed if you have cards from 1 to 99, because you probably weren't going to use card 100 anyway. If you're not going to use card 100, then you've got 99 left, which is a sort of smaller problem. Of course, this is going to fail at some point, right? We can't just say that all of these are equal. It feels like I'm getting close to saying they're equal. I have the number of ways to do it with n cards. It's pretty much the same as the number of ways to do it with n minus 1 cards. Obviously, that goes wrong. It goes wrong constantly, but more and more wrong the fewer cards you have. The more and more likely it was that you kind of the intuition is that the more and more likely it was that you are using card N actually. When you get down to 5 or 6 cards and you're having 4 in a row, well, you probably are going to use the last one. That ever become actually true? As far as more than 50%? Doesn't matter, not important. My language might not quite line up with the actual percentages, but never mind. Right. Else, maybe you pick N, but not N minus 1. That's quite bad. You must now, so if you choose card 100, number 100, but you don't pick 99, then that's annoying because now you've only got 98 cards left, and you still need to get 4 in a row, and you've wasted a pick because card 100 wasn't helping. You must now get 4 consecutive numbers out of k minus 1 integers chosen from 1 to n minus 2. My handwriting is getting worse the faster and more excited I'm getting about solving this problem. So there's another case. So else maybe you choose n and n minus 1, but not n minus 2. So then you have, so this previous case you're choosing k minus 1 and you have n minus 2 numbers to choose from. So I should write down n minus 2, k minus 1. And then you have, you're choosing n minus 1. Maybe you pick n and n minus 1, but not n minus 2. So then you have n minus 3 numbers left, and only k minus 2 picks. And only a couple more cases here. Maybe you pick, you can kind of see what I'm doing, right? It's bad if the card N was picked but was part of an unsuccessful sequence. That's quite bad. You can still save things. You get actually some more ways to do this, but they're pretty unlikely, I think. So then you have n minus 4 cards left because you didn't pick card n minus 3. And you have k minus 3 picks to make this work. Or, and this is the last case, maybe you pick n minus 1, n minus 2, n minus 3. You get your sequence right at the end. And in that case, it doesn't matter which of the n minus 4 remaining cards, numbers or whatever, are picked. I should be saying cards all the way through. Right, something amazing happened there. A spammer came into chat. Did you see a spammer came into chat? Got banned straight away by the auto moderator. That's the first time that's happened, which means that instead of stopping during a good bit of casework, going through the different cases, instead of stopping to go and ban someone, get wrecked. I hope that wasn't one of you just saying one of the banned words by mistake, but you know, we did it. Managed to keep doing maths. Maybe you can do maths on Twitch. Hurrah! Everyone thank Automod. Great. Good job, Streamlabs. Yeah, I've never heard that username before. Oh, I think it's not one of us. Right. Yeah, don't get banned for being a bot. The ban word, in case any humans care. Let's double check what the ban word is. We noticed that all the bots were using the same word. I almost shouldn't tell you, right? But, oh yeah, it's a word starting with V that refers to people who are watching. That's the only thing that's banned, I think. Maybe there are others. Yeah, we've banned in chat the word to do with people who are watching the stream that starts with a V, because all of the chatbots wanted to give us more of them. Is anyone who got banned as a joke? Yeah, that's the phrase. That's the phrase that we don't have anymore. Can't double check it. Good. Don't test it. Don't test it. As far as I know, it's just working now. Yeah, there you go. Right. You get timed out, I think, rather than banned. Right, learning about Twitch. That's fun, isn't it? I think this leads to a recursion relation, by the way. A relationship between all the possible hypothetical cases about whether you use card N or not. So there are some where you make a string of 4 consecutive numbers right with those largest numbers, in which case it doesn't matter, you can pick whatever you like. Lots of ways of doing that. And there are some cases where you start making a consecutive set of 4 with the largest numbers, but then it goes wrong, which is quite, get some ways. There are still some ways that you might succeed with the smaller numbers, but in here, like the final one was if you don't pick anything near the top, then you're using smaller numbers at all. And there's kind of several different cases. What is that? 1, 2, 3, 4, 5 different cases, corresponding to a string of consecutive numbers near the end, including n, of length 0, 1, 2, 3, 4 or more. Those are mutually exclusive. So I think this works as a way of splitting down the cases to say, starting with n, read backwards to see how many numbers there are in a row. It might be 0, it's probably 0. 0, 1, 2, 3, or 4 or more, which is why the first case and the last case feel a little bit different from the middle ones, because 0 is a bit different. I guess it gives me the same sort of term in my equation. Equation is going to be, so I think the number of ways to pick k numbers from 1 to n such that you have a set of 4 consecutive numbers is f of n minus 1 k. You might be choosing k from n minus 1 of those numbers and then not picking number n. That would work. Or you might be choosing k minus 1 from n minus 2 numbers, and then one more, you pick number n as well. Going backwards and forwards on whether I think n is 100 or not. It's kind of quite useful for the explanation if it's 100. And there's a plus over here. And the plus is going to be a little bit controversial, because I think if you choose these 1, 2, 3, 4, then I don't care about which of the other n minus 4 you pick at all. Maybe you pick n minus 4, maybe you don't. Maybe you sort of pick the smallest 8 numbers or whatever k minus 4 is. But you've got k minus 4 picks to left, and I don't mind. So if you like, this is counting a bit like Neutrino's idea of way of saying it. It's counting for each success with 4 consecutive numbers, find the largest number in the largest set of 4 consecutive numbers, and reason from there. Almost, not quite. It's not quite that straightforward. It's still pulling together previous cases. I think I want this n minus 4 choose k minus 4 corresponding to this last case. You've got, out of n minus 4 numbers left to go, I really don't care which k minus 4 you pick. I've already won. I've got these 4 numbers in a row at the top. So anything goes. They could be spaced out, they could be together, and because we're trying not to double count, we should count each of these things once. Okay, I think this gives us a recursion relation that kind of works. It relates together the value here, with n and k's, to smaller values. I'm not sure how convincing I am about it, but I'm being quite cautious. In general, if you're looking for something of size larger than 4, if you're looking for a string of 5 or more, then I think you can change this number. So the 4 that I didn't change, you can change it here, and then it's in the number of terms here, and how far they go, subtracting each time. I think it works. Cool thinks it works. We should test it. Let's test it on some small numbers. So as a check, we're going to do. We're going to check f. I'm going to go for 5, 4, maybe 6, 5, something like that. Small numbers. I should check some larger numbers as well, like 10, 5 or something. But I might need a computer by that point. Luckily, I have a computer. Okay, so this would say that f54 is f44 plus f3433. I'm supposed to decrease k on that one. And these are all going to be 0 anyway. So maybe checking small cases is not that good, because if one of these is wrong, then I'm going to write 0 anyway. F of 2, 1, f of n minus 4 is 1, k minus 3 is 2. What have I done wrong? K minus 3 is 1. This is k minus 2, which is 2. I missed out the number 2 in between 1 and 3. Newsflash, there is something in between. 1, 1, plus, and then this n minus 4, 1, choose 0. So maybe these small numbers are not the best example, right? So f44, I know that if the first and last numbers are the same, the two numbers are the same, you get 1 using the fact fnn is 1, which maths 2 to 2 to 2 told me. And then these things are all 0. Pluses. 1 choose 0 is 1. That's going to annoy people, isn't it? The number of ways to choose nothing from a collection of one object is one way. It's the top row of Pascal's triangle. If you know Pascal's triangle looks like this. This thing means the number of ways to choose one thing from a collection of 1. This thing means the number of ways to choose 0 things from a collection of 1. There's one way to do it. In this example, it represents the case. This one represents the case where you selected white circles for selected, I suppose. You selected the top 4 numbers. Yeah, and then out of the remaining numbers, I need you to select no more, because we've already got our 4 picks. K is 4. So the number of ways to select nothing from here is just one way. It's fine. Just don't select it, and then we'll be good. We've got 4 overall. Whereas this one refers to the case where you don't select this top thing, and then you must succeed using the remaining 4. Yes. Yeah, so the F44 case lines up with one where we don't select the top thing, and this one lines up with the one where we do. Yes, so numbers 2, 3, 4, 5. Yes, good. Let's think about F64. Choosing 4 is a bit boring because they have to be in a row and they're the only 4 we pick. So maybe I should think about F55. Well, I suppose that's 1 for boring reasons. It's 1 because it's on the diagonal. Rubbish. Maybe I should think about F, just to check it's working. I kind of want a larger number here. So maybe I should be brave and go for something like 7, 5 or something. So in my head quickly, you're choosing 5 of these and you want 4 in a row. And if I do my normal method from before, the method that doesn't work, I would have some overcounting effect, because I might choose 4 and a loose one, or I might choose 4 and a loose one, and that's the same set of first 5 numbers. So my old method would give me something like you're permuting 4, 1 and 2 blank ones, which is 4 factorial divided by, okay, right, divided by 2 factorial, which is 12 or something. This is going to give me the right answer though. It says confidently. So this will be f of 6, 5 plus f of, and then I'm supposed to subtract 2, 5, 4 plus f of 4, 3 plus f of 3, 2. I see, so subtracting 1 each time is maybe the way I should be thinking about this. Starting with the same value of k. Okay. Plus 3 choose 1. And that 3 choose 1 at the end refers to the idea that you might have the numbers 4, 5, 6, 7 in your set, in which case it doesn't matter if you throw in 1 or 2 or even 3. Good. So I think I need to do something with this F65 as well. I'll split that out in a second. We already found out F54 is 2. F43 is 0, because if you're just choosing 3, then you're not going to get there. And then 3, 2 is 0 as well for the same reason. And then 3 choose 1 is 3. So let's quickly expand F65 and then add 5 to it, and I think we'll get something that we can make sense of for F75. Gosh, I've picked large numbers. Let's see if we can check this number. So F65, our rule says that you take 4 sub-problems and add them together, plus a fifth case where you just do some choosing because you celebrate that you've already won. So then it's all over. And we're going to then add 5 for this 2 plus 3. 2 plus 3 is 5. Welcome to Chill Maths. So this will be 5, 5. Smaller numbers. So then I go down like this, I think. N minus 1k, and then subtract, subtract, subtract. Most of these are 0. That's 1, that's 1. This is supposed to be n minus 4. Choose k minus 4 to choose 1. So this is 1 plus 1 plus 0 plus 0 plus 2 plus 5. That looks like the Catalan numbers. Oh no, that looks like Catalan numbers. It's probably not. It's probably a coincidence. Which is 9. So ideally, I would now demonstrate that. Oh my goodness, look at that. Timing on that one. 1, 2, 3, 4, 5, 6, 7, 8, 9 of them in chat. Thank you very much. On my wavelength. Oh, and you've got them worked out. Are they kind of in order? Is that a computer search or just a very good human search? So you're stepping 1, 2, 3, 4, 5, or you might choose 6 or 7, and then you've gone, okay, those are the ones where you choose 1, and you get your string of 4 over there. You might have your string of 4 starting at 2. Yeah, sort of systematic. I like it. Yeah, I like it too. That seems good to me. You can start from the left end. I've been starting from the right end and arguing about using the numbers n and down. You could argue about using numbers from 1 and upwards. This one's odd because, oh dear, why is this one odd? It feels like maybe there's a mirror symmetry thing going on. So each choice you make, there's a mirror symmetry one which you can make. This one has worked out to be an odd number though, because is there a mirror symmetric way to choose 5 things from 7? Yes, there is. Choose the middle 5, and then we'll have a sequence of, that will have a subsequence of 4. That's in your list, isn't it? 2, 3, 4, 5, 6. It's kind of the odd one out. It's, yeah, there we go. Symmetric with the other side. Here's what I wanted. Sense checking my method against people in chat. Yeah, other people joining too. I feel like I'm just talking to a call for a moment there, but it's good. Good. Okay, we've got 9. My plan is to now write some code to try and actually do this because I think this works. It relates each one down to previous values, but 112 are quite large, so I was going to write some terrible computer code to try and do this. I think the trick is to build upwards. I had a go at this before and built downwards, and that was bad. Here's as far as I've got on my terrible computer code. It's in MATLAB, the only language I speak. Okay. So I think the trick is to fill in a matrix as you go. I should probably call this F or something for my values, so that then I have MATLAB language. F of 112 is the one I want. So I'm initializing it to zeros because most of them are zeros, but we should put the 1s down the diagonal. So let's put in these numbers properly. Let's give these names. It's not a chill math stream without a terrible code. In this case, written in MATLAB. Have people seen Matt Parker's recent video? It's really good. Matt Parker and Steve Mould have done something cool with AI generated art. Although there is a comment that says maybe we should give this to some human artists to see if they can tweak it a bit more and make it more human using this as a kind of template. But they've done something interesting with AI art. They've involved writing some pretty weird code. It's generated this image that rearranges. So if you trick the computer into drawing an image, changing your mind constantly about what the image is, then you get an image that kind of looks like both of them. And for Matt Parker and Steve Mould, that is an image, and then a manipulation of that image. So you manipulate it and it turns from one thing to another. Recommend the video. It's a good one. Right, I'm stalling for time because I need to go. So this is going to be where I regret going from. This is where I regret going for general numbers because now I have to type them all the time. So instead of just going item 12, so this one is supposed to be 0. It's supposed to be 1. There is one way to do this if you select all of them, and that is to select all of them. And then I've got some zeros if k is small or n is small, which yeah, so Taurus and Mug are the two images that they made in Matt Parker's video, which I liked. A lot of human picking as well. They had to generate quite a few. Right, okay. There's a combinatorics problem in there, which probably... Along the way, Matt had to solve a combinatorics problem to do with jigsaw puzzles that was also brute force with computer search, which I feel like maybe there's some maths in there that you could do. I don't know. It'd be nice. I think it'd be nice if the puzzle rearranged in some really tidy way. That's not what they wanted, but I guess the thing I would do is something like rotate the pieces, take 4 of the pieces rotationally symmetrically and spin them, and maybe spin a different set a different direction, try and set up the edges so that all works. And then maybe there's 2 ways of doing it. So now I try and build something like that, I think. They did a computer search to try and find something where there's only 2 solutions. It was a jigsaw puzzle. I'm telling this story in a very strange order. I haven't decided quite how much of Matt Parker's video I want to steal for my Twitch content. Right, before we become one of those Twitch streams that just reacts to other people's YouTube videos, let's type some code. So, I would like to go from k is 1 to k max, and for n is, well, maybe actually I only want to go from 4 because that's the only one that makes sense. N max. Maybe I want to increase n on the outside. It maybe doesn't matter, but I think I'll be happier if I do it this way around. So k 4 to k max. I would like the following. K should only go up to n. There you go. Okay. I only care if k is actually as most as n minus 1, because if k is n, then I've already done that case up here. And if k is larger than n, that you're trying to choose from, you haven't got enough numbers to choose from, so it's 0, which is how I initialized it. This line is initializing it to say, give me loads of zeros in a matrix. Okay, I guess I type my formula in here. Yep. That's the nice thing about that, you can sort of just get on with it. Plus, let's go line continuation, just to be fancy, rather than doing one massive line. The check here is whether I'm typing the right stuff. 1, 2, 3, 4 cases. 1, 2, 3, 4 cases that should be like this. 1, 2, 3, 4. No, something's not right. 1, 2, 3, 4. 1, 2, 3. Quick look back at what we actually wrote. 1, 2, 3. 1, 2, 3, 4. Yep. Okay. And then plus, I think that, yeah, it's this, isn't it? n minus 4, k minus 4. Okay. So maybe if I run this, it will now loop through different values of n, and it will look back, just look at previous values of n, or except for, yeah, previous values of n, so everything's all right. It will look back. Lando won it. Yes, nice job. Leads lap 1, keeps the lead. Good. Max second, fastest lap. He's won it. We need 8 points for Lando to. Lando wants 8 points. I guess the spicy thing would be Max in second place. Max fastest lap. That'd be fun. Because that'll be a 6-point swing, which is statistically not enough. For those who don't know what we're talking about, Formula 1 is in this kind of weird mathematical place where they have huge numbers of points that you can score. You can only score a few of them each week. So there's this sort of slow progression of point scoring. There's this bound of mathematical possibility. As we get to the end of the year, it's all closing up. Managed to tell the story of the Formula 1 title battle without mentioning any humans. Fastest lap, not Max. Also not Lando. Those are the humans. Right. I'm going to run it and see what happens. It's unhappy. That's what happens. Must not exceed 12. Why is it exceeding 12? Oh, okay, so I only care about, I'm going up to n minus 1. So I've asked it accidentally to calculate 5, but that's not relevant if I only care about 12. So I should only go to Kmax. What do I want then? So I want this to be something like the minimum of Kmax and n minus 1. You stop for either reason. Now it's more happy? Unhappy? Just run. At the end it should have a kind of matrix for f. Let's have a quick look. What's it done? It looks like a matrix with some numbers in it. It's got these ones on the diagonal. It's the other way around to my diagram earlier. It's got this kind of interesting sequence. If you have 4, so this is the sequence for n is 4. No, which way around is this? So it's not quite the counting numbers. So this will be something like if you have more and more numbers, yeah, n and then k, and you pick 4 of them, jumping up to 5. So this is 4, 4 is if you have 4 numbers, you choose one. There are one way to win. If there are 5 numbers and you choose 4 of them, I don't think there are 5 ways to win. I don't think there are 5 ways to win. This would be 5, 4. 5, 4 is one of the ones we calculated, isn't it? We think 5, 4 is 2, not 5. So let's analyse the code and see what's going wrong for 5, 5. So for 5, 5, it should be looking at 4, 5. Something's wrong there. Have I done all of this wrong? 5, 4, it should be looking at 4, 4, n minus 1k. N minus 1k. So for 5, 4, it's looking at 4, 4, which is the number 1, plus, and then all of these should be 0. All of those should be 0. 4, 4, which is 1. And then looking at subtract 1. Oh no, that's looking at 3, 3. For this 5, 4 case, it's looking at 3, 3. 3, 3. So in here, my mistake is that the thing in chat, somebody said that fnn should be 1 only if n is larger than 3. Yeah, there's a mistake. Okay, run it again. Have another look. Yeah, there we go. Now it's counting numbers. That's a bit better. Oh, it was such a weird sequence. It's worth looking at your numbers. So now it's got true facts like fn. If n is 5 and k is 4, you're choosing 4 things from 5. Do you get 4 in a row? Well, only if you pick the first 4 or the last 4. If you're choosing 6, you get these choices about where do you start, which is the counting numbers. And then this is some complicated combination of the previous things. And what I want is f100, 12, which is over here. That is, is that slightly too long for my... Can I get that number out? It's slightly too large. I want for long. Slightly too large for full precision. That is annoying. I'm 16 digits, right? Squares. Oh, did you see some squares? What are the squares? There are squares in here. That's a very good point. There are some square numbers in here. That's a very suspicious point. Oh no. And these look a little bit familiar as well. Why are these squares? Okay, it's a good observation. If you're choosing 5, looks like the answer is a square number. Hypothesis, n minus 4, n minus 4. So is f of n 5 equal to Okay, good question. I like it. There's probably some counting argument you can do here. That'd be crazy. Why is that? Why would that be true? That'd be great. Square numbers. I mean, what on earth are these? I feel like I've seen these before. Probably I should put these into OEIS or something. 1, 6, 18, 40. Back in a second. OEIS. What were they again? 1, 6, 18, 40. 75, 126. 126 is a Catalan number? Oh no, they're the pentagonal pyramidal numbers. N squared, n plus 1 over 2, which looks suspiciously like, where's a polynomial of degree 3, isn't it? With some nice factors. So maybe this last thing is a polynomial of degree 10 or something. Yeah, right. Is this one of the examples? If not, maybe we should submit it. Oh my goodness, there's so many examples on here of what's going on. Does it say anything 4 in a row anywhere? I think it does. It is n times the nth triangle number. And the previous thing was n times the nth number square. If this is just n times n choose k minus 4 or something, that would be very annoying. Maybe checks out. There might be multiples of n. That would be very annoying. So the next one down. So this one we spotted was squares. This one is n times the triangle numbers. Right, so can I just paste these into OEIS? That'd be nice, wouldn't it? Yeah, more or less. Yeah, n times the binomial coefficient. This is what I was scared of. Yeah, I don't care about this 4-dimensional figure stuff. There's that formula that's just n times a binomial coefficient. Yay. This is looking like that it might just be, let's put this on second monitor, go over here, is fnk equal to, and then what do I think is going on? So I just pasted in k equals 7, and it came back with m plus 2 or something, but we're shifted by some amount. So this is something choose something where both of those depend on k. 7, so this is like k minus 4 or something. And this thing up here is I think it's maybe n minus 4 that I mean to write over here, because the sequence starts at, I'm copy pasting it, but it's got a load of trailing zeros at the front. So it's out by several. So there's a factor here that this is when k is 7. So this is something like, yeah, okay. So k is 7, this is when n is 7 and k is 7. You want this number to be 1, 2, 3, which is n minus 6, because minus k, sorry, n minus k plus 1 or something. Oops, lost the bottom of my board as well. n minus k plus 1. So then n minus 5 plus 1 is consistent here. And then I think this would be, so this would be n minus k plus 1. And then the next thing that we're looking at is, we think this was n minus 4. So also this. So possibly this as well. Maybe plus another 2 or something. Maybe plus another 2. Maybe plus another 2. Because then here it will be, check it for a big number, yeah. So I'm trying to get my out by ones correct. Some coefficient. It just told me this was binomial n plus 2 choose 3. And then the argument is going to be, can we find, and I believe there might be out there somewhere, some stars and bars method for actually checking this. So I'm going to go for something like, Or just check the recursion relation, right? If the recursion relation checks out, then it might be fine. There's also lots of out by fours, so I have to be a bit careful that we're not just looking at the first 4 numbers of a sequence and spotting something that goes away. But no, that is true. So this one's squared. I feel like if we could understand the squares here, after 4 zeros at the top, just getting square numbers, if we could understand squares, we might be almost there. So that might be a good thing. Let's see if I can do... So very quickly, because I want to stop in a minute, I think. N max for j equals 1 to k max. And I want this new thing that is the same size as f. A cheap way to do that in MATLAB, well, a cheap way in terms of thinking, is to just multiply the thing by 0 to initialize a 0 matrix of the same size. It's not good code. But here we are. So I think I would like to think about... this thing being n minus k plus 1, I think we said, times, and then n minus k plus 1. This is going to be unhappy with me. What did I want to put over here? This scribbly bit of MATLAB, k minus 4 possibly. It's choosing more things as you go to the right, k minus 4. Something like that. It's going to complain at me, isn't it? Because you can't make that number large. So I shouldn't make this larger than... I shouldn't make k larger than n, otherwise it will cross with me. Still cross with me because I'm starting k from too large. I should only start k at 4. Still cross with me because I guess there's getting some weird thing going on here. So right side, left hand side, 1 by 1. I don't know what it means. It's just crashed at a point where n is 1 and k is 4. N is supposed to be only as large as this. Still cross with me. Might not get this working. It's supposed to be just a quick check. So now it's crossed with me. N is 6 and I is 12. And n is 6 and k is 6. So it's trying to calculate 1, choose -2. Rats. N is 6, take away 4. 6 is 0, 1, choose. Is it not just happy with this? I guess 1, choose 2. I want it to stop, I suppose, when you get to n minus 1 or something. I don't want k minus 4 to be larger. There's no point getting this larger, so maybe I should put in. Well, let's put this in for now and see what happens. Still cross. No more cross A and 7. Yeah, n minus k plus 1 is negative for some of these, which is annoying me. Maybe I'm supposed to start this at 5. Maybe I'm supposed to start this at 4, I don't care. Sorry for all the plings as I flail and throw at random numbers. What does it want? What does it want? I just want this sequence, right? Just trying to do this sequence. When n is 5, when k is 5, for n is, I guess, 5 up to n max, I would like to just look at this sequence. And it's happy with that to give me this sequence with the square numbers in it, which is great. So now I would like to think about, very carefully about 6. Is it going to be happy? It's unhappy with me now, because if I go up to 6, then it gets cross when n is 5, because 6 is larger than 5. You can't go larger than 5. So it's whether this thing is negative or not. So I'm supposed to stop at n minus 1, I think. Still not happy. Still not happy. Is it writing any of this? Oh, it's worse, it's writing that way. It's writing in 7 and stuff. 6, but I want to stop earlier. Something like this, but put the ends, swap the loops, and go up to nightmare stuff here. Stop if you get to k minus 1. Still unhappy. Hasn't written anything. Between 5 and 6, so it goes up to k is 6, and it's already given up because it's tried to put in 5 take away 6 plus 1. It's got 0 at the top. It's complaining about this thing. Oh, it's too large. Why is that too large? Right, okay. New idea. Just tell it to only write it if it's happy. This is so clunky. Greater than 0. And we'll put another safety check in. Let's put an and in there as well. K minus 4 is less than n minus k plus 2. It's got to be later. It could be equal. That'll be fine. Then you're allowed to calculate this. So be happy. Otherwise don't. And we've defeated all of the error messages by only writing in the ones where it makes sense, and we've generated an interesting table of numbers. They're not the same as the numbers. The squares are the same, but then I've somehow messed up these. I've got nothing in the 6, 6. I've got 2, 9. So my formula's not quite right yet, which is possibly why I got so many error messages. What do I want then? It was worth a try. Worth a try. I've managed to write square numbers next to numbers for my guess about what the formula is, but I haven't generalised it well. I haven't even got that behaviour where we saw in the 6 column. In the 6 column we had these things which OEIS told us were n squared times n plus 1 over 2. That's because that is increasing the top. N minus k plus 3? Yeah, let's try that. Let's try adding 2 to the top number. Okay, so that should not error too much. And now it's wrong in a different way, which is fun. Now I've got the squares wrong as well. And moving things around with reckless abandon. Oh yeah, because I didn't want to change that. I wanted to change the other one. This one in the choose, not the prefactor. Now run it. And then I think it should get the squares. Yeah, so it's still getting the squares wrong. Still getting these numbers right, but I'm getting these squares wrong. I'm close. There's some sort of binomial choosy thing multiplied by a n shaped thing. I think I'm going to stop there. Sorry, but I've got to run. Rubbish. Okay, right. We're going to leave this as homework. I think. Homework. I think if you want to play along, is something like fix this. I'm out by something. And 2 is something like y. And I'm going to be back. Rubbish to drop it there. That is a cliffhanger. I'm going to be back next week to try and work this out. Yeah, good. Right. Take care, chat. You got some homework. Maths 2 is very keen. The code is not hard to run. If you would like to look at the numbers, the correct numbers that we're trying to explain are these. We spotted some patterns. I haven't been able to write down the patterns correctly, and I haven't been able to even start to explain what's going on there. Challenge for another day, but got to run. Take care, chat. See you next week. Yeah, sorry. Good. I love it when it looks like there's more research needed. It looks like there's a pattern. I was not expecting to tab over. I'm going to make a little highlight, I think, possibly tab over and see, I know these numbers. I recognise this. Oh no. Right, there's something going on here. Leave that to you, and I'll see you next week for more Chill Maths. Bye.